Welcome to lecture 12. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course Geosynthetic Engineering in Theory and Practice. Now begin Module 3, Lecture 12, Geosynthetic Properties and Test Method. Recap of previous lecture. We have covered puncture resistance test, penetration resistance test or drop test or tear resistance, tensile behavior of Geogrid material, Geogrid rip tensile strength, Geogrid junction or node strength, junction strength of geocell, tensile strength of gabion, and direct shear test on geosynthetics. Now we will discuss the pullout or anchor resistance. It is very important to compute the pullout capacity of reinforcement to ensure stability of any reinforced structure like reinforced soil retaining wall, reinforced slope, etc. Now, in case of pullout test, two basic mechanisms are involved to mobilize or transfer the pullout resistance between soil and geosynthetics. One, interface friction, and other passive resistance. Only interface friction is associated with geotextile or metallic strip or para wave or friction tie, etc. Both interface friction and passive resistance are associated with geogrid. Pullout resistance and anchorage capacity is expressed as the ratio of pullout force to the width of the sample, that is kilonewton per meter. Now I will discuss what is interface friction and what is passive resistance. For example, if this is one layer of the soil and then you place this any metallic reinforcement and then you place another layer of the soil and then you are pulling, you are applying some kind of load, you are putting some applied some load and then you are pulling this, okay, pulling. So this is pullout test. So you, what is happening? And this also may happen in case of the metallic strip like this, or you can also conduct the test like geogrid material also. The soil is top and the bottom and you apply load and then you are pulled it out. So if it is a metallic strip or it is a kind of open or the non-open geotextile like this, so there will be a development of friction. And how the friction developed? So let us consider the metallic plate like this, and soil is at the top and the bottom, and the normal pressure is acting, and this is the normal pressure. So you can say this is normal pressure. All are normal pressure. These are all normal pressure. Similarly, normal pressure. This is all normal pressure, and this is the reinforcement. This is the reinforcement. This reinforcement may be steel strip, it may be the steel strip, or it may be the polymer fabric, or it may be the paraweb, or it may be any plastic strip. And then you are pull it out. This is pull out force. Pull out force. If this is the reinforcement and normal pressure is applied here, and then you pull it out. If you pull it out, then there will be the development of frictional force. This is frictional force. Okay. So this is the frictional force will develop. So this what we call frictional force. So you can see that how the frictional stress transfer between the soil and the reinforcement. Now this friction, that means stresses are transferred from soil to the reinforcement by shear along the interface. So you can see that how the friction force is developed between the soil and this reinforcement. Now this is particularly in case of any metallic strip or any paraweb or any plastic strip, etc. Now second part is the passive resistance. So for example, that this is a Geogrid material. You can see that if you pull it out, there will be a development of frictional resistance and as well as passive resistance here. So I am just showing this, how this development occurred, that frictional resistance and passive resistance. Let us consider this is a kind of the material, and like this, let us say it's like this, and you are pulled out. This is pull out force, or you can say anchorage. So this is pull out. Pull out force. So you can see here there will be a development of frictional resistance. This is frictional resistance, but this portion there will be a development of passive resistance. This is passive resistance. So you can see in case of the geogrid material, there will be a development of, this is what we call frictional resistance. And as well as there will be a development of passive resistance. Passive resistance. So you can see in case of the geogrid resistance, when you pull it out due to some applied load, so there will be the frictional resistance developed between soil and this reinforcement material. So this is the reinforcing material. Basically this is the reinforcement material. It may be geogrid. This is reinforcement. So when it's pulled it out, so frictional resistance and the passive resistance. So every geogrid material also has a longitudinal direction and also transverse direction. So let us draw a geogrid material, say like this. And whole thing you are putting pull out force. And geogrid material has a transverse rib and also longitudinal rib. So this is the transverse rib. Transverse rib and also longitudinal rib. Longitudinal rib. Now, due to the pulled out, there will be a development of the friction and as well as the passive resistance. You can see there is a development of passive resistance here. There is a development of passive resistance here. Also, there will be the development of friction. You can see there will be development of friction. There will be a development of friction. So you can say also here also friction, here also friction. So these are the frictional force and these are the passive resistance. So this is the passive resistance. And these are the frictional. Frictional, this is resistance. So here we are showing that soil passive, that means bearing resistance of reinforcement surface. So passive resistance means stresses are transferred from soil to the reinforcement by bearing between the two transverse element against this soil. So when you pull up the material, most of the part of the load taken care by the passive resistance, or what you call the bearing resistance, rather than the frictional resistance in case of the geogrid material. So now you have some idea about what is interface friction and what is passive resistance and what kind of the material where you can perform the test for the interface friction as well as the passive resistance. Now I will show that some pictorial view of the pull-out test, and this is the schematic diagram. You can see that here is a geogrid kind of the reinforcement which is pulled it out, and on the top and the bottom, on the top of this soil you are provided with the rubber, a kind of the balloon on the top. It is a rubber. This air pump is tightening with the pump in the rubber, and then you are applying the load, because if we provided with a kind of the air passage bag, then the load will be distributed uniformly. So that's why the reason this is very important that you should provide proper kind of the air passage bag on the top of this soil. And also in this back in the front, this back you can provide with a kind of the geofoam material, because there is a possibility of development of any earth pressure. So if we can place a very thin layer of the geofoam material, it can reduce the lateral pressure. That way you can perform the proper kind of the pull-out test. So in case of the pull-out test, very important is that interaction coefficient of geotextile material, which is denoted as C of I. For example, that this is the geosynthetic material and this is the PR, and this is the normal load is sigma n. So you have to calculate what will be the P of R, pull-out force. That is, what should be the pull-out force if that pull-out force is the F, and if you know what should be the width of the sample. So you can calculate what will be the P of R. You can see that you can determine what will be the P of R. So this PR is equal to 2 into L into sigma n into Ci into tan pi. So Ci into tan pi is like a tan delta, and sigma n is the normal stress. So if the gamma is the unit weight of the soil here, and h is the height from the geosynthetic material to the top of the soil, so then you can determine what is sigma of n. That means this sigma n is equal to gamma into h, and there will be a surcharge load, and let us say that surcharge load into sigma of q. So you can write sigma n is equal to gamma into h plus surcharge load is sigma q. Now why it is 2? Because the shear stress is acting at the top and bottom of the geosynthetic material, that is why 2, and this is the length, embedded length. So 2 into L into gamma h into sigma q into tan of pi. So Ci can be determined PR divided by 2 into L into gamma h plus sigma q into tan pi. So this is pi is known to you, so you can calculate this, what is C of I, interaction coefficient of geotextile material. So this is another FEM analysis of pull-out test on cellular reinforcement. Here we have considered a kind of the cellular reinforcement. So cellular reinforcement, what is cellular reinforcement? So it is a made of plastic, it is a bottle, it may be hexagonal, it may be web. So this, and then connected with the another cellular element, it can be connected like that. You can also produce a kind of the cellular reinforcement. This is a very good confining effect, and then fill up with the soil, and then you can pull it out, because give the very good confinement effect also. Also we will determine if what will be the height you can optimize, and you can place this kind of cellular reinforcement for the construction of the wall at a particular spacing. Then we can optimize and can determine what will be the height and what will be the spacing, and how we can optimize that. That also we will focus. Here one of the student research scholar Dr. Khetgar have carried out some test on the cellular reinforcement. You can see that when it is pulled it out, then you can see how the distribution of the stresses here. This is the stress distribution in a cellular reinforcement, and he has conducted the finite element analysis for pull-out test on cellular reinforcement. Now ultimate pull-out load was found increasing with the increase of the height of the reinforcement up to 30 millimeter. Further increase in the height shows the decrease in the ultimate pull-out resistance. So optimization analysis shows that the spacing to the height ratio of 3.3 gives the maximum pull-out resistance of cellular reinforcement. So you can have the idea that what optimize. So height to the spacing to height ratio will be 3.3. Now we are giving one example. So you have to determine what will be the interaction coefficient, that means Ci. The following data is given. P is 65 kilonewton per meter, Le is 1 meter, pi is 30 degree, Q is 60 kilopascal. You can see here is pull out, P value is given, and this is the reinforcement. This length is equal to L of E, and this is the height. Height is about 0.3 meter, and gamma unit weight of soil is 20 kilonewton per meter cube, and pi is equal to 30 degree, and you put something surface pressure is Q, and surface pressure Q is given 60 kilopascal. Height is given, that is 0.3 meter. So what will be the load? Sigma H is acting here. So sigma H is equal to gamma into H. Gamma is known, that is your 20. H is known, that is 0.3, plus surcharge load Q. Q is given 60. So if you calculate, you can determine what is sigma N is equal to 66 kilopascal. Now we know the equation P is equal to Ci Le sigma N tan pi. So P is given 65 kilonewton per meter, 2 into Ci into Le is 1 meter, consider 1 meter, into sigma N into tan pi. Sigma N is equal to 66 kilopascal, and tan pi is equal to 30 degree. Pi is equal to 30 degree. So you can calculate the Ci. Ci is equal to 66 divided by 2 into 66 into 0.587 is equal to 0.849. So interaction coefficient Ci is 0.849. This parameter is very important when you will design for any mechanically stabilized reinforced soil structure or the soil stability problem. Next, we discuss the tensile behavior of geomembrane. So you know that geomembrane is an impermeable material. It is like a rubber, and you have a smooth high density polyethylene which you call HDPE, and structure high density polyethylene and geomembrane are also used for conducting the dumbbell shape. So it is a dumbbell shape test. So you can see here, this is the pictorial view and this is schematic view. So you can perform the test as per STM D638 or D682 or D6693. You can see it is a dumbbell shape, and test specimens are cut from a large sheet. So this you can see that is 350. So you can see that all dimension is given here as per the STM D638, and then you can conduct this test universal testing machine, and you can calculate that what will be the tensile strength of the geomembrane. Look at this picture. This is tensile behavior of dumbbell shape geomembrane. This is the force and elongation, and this the dumbbell shape is textural and also the smooth. You can see that force is increasing, elongation is very less, and then it is decreasing, then it is constant, and then again it is increasing like this. So it may goes to 400% strain, 500% strain, and also it can goes 700, 800, 900, 1100%. So there are different types of the geomembrane. It may be high density polyethylene, it may be PVC, polyvinyl chloride, but it is very important what should be their tensile behavior. So I am showing here that if it is a high density polyethylene geomembrane material, and tensile says has to be conducted whose specimen size is about 200 millimeter wide and 100 millimeter gauge length, and strain rate is 1 millimeter per minute. So this is wide width geomembrane test. So tensile behavior of wide width shape geomembrane is suitable in plane strain condition and much more design oriented compared to the dumbbell shape geomembrane. So you can see here the tensile behavior of wide width shape geomembrane, smooth and textural geomembrane. So greater width of the specimen minimize the contraction edge effect, that means necking, what you can see here, and provide closer result to actual material behavior. This is as per STMD 4885. So you can see that some of the result of the smooth and textural behavior, and which thickness of the HDPE is 1.5 millimeter. This is the strength at yield, and this is as per STMD 638, and dumbbell shape you can see this is 30.3 kilonewton per meter, textural strength 27.7 kilonewton. If it is a do narrow with 25 millimeter STMD 882, then strength at yield 28, this texture case 27.54, wide width 200 millimeter STMD 4885, smooth 26 and texture 24. And elongation at yield, in this case 10.4 percentage, this is 9.6 percentage, this is 16.5 percentage, this is 15 percentage, wide width case this is 15.5 percentage, this is 15.0 percentage. And strength at break as per STMD 638 is 28.19 kilonewton per meter and 29.5 kilonewton per meter. But elongation at break is 435, 358, it is all greater than 500 percentage. So you can see that how the strain value is increasing. This has also some beneficial effect for the use of this kind of the geomembrane. Now I just wanted to explain about some tensile stress versus the strain response curve for HDPE and the PVC. For example, this is the stress, this is kilopascal, and this is the strain, this is in percentage. So if it is a high density polyethylene, this curve goes like this and then goes like this, then it is increasing like this. So this is the high density polyethylene, say a kind of ductile behavior. But if we perform the test, tensile stress, and obtain the tensile stress versus strain response curve for the PVC, you can see that this curve goes like this and then it suddenly drop like this. So this is the kind of material you can say PVC, which you call the polyvinyl chloride. So this also brittle behavior, that means it's sudden failure. So you can see there are two types of the material, one is the HDPE, another is the PVC. So you can see that you require the stress and you require the strain for a longer time, it gradually is increasing. What you can use the high density polyethylene material for the construction of the landfill problem, where you are dumping all kinds of the waste material year after year, and then you require for elongation for the longer time. So there is no failure. You can observe there is most of the cases no failure in the high strain value. On the other hand, you can see that if you use PVC, then it may suddenly break. It may give the high stress value, but strain is limited. So you have to be very careful what you wanted to use the HDPE material, what you wanted to use the PVC material. So depending upon the type of the problem, what you require, maybe the strain, not the elongation too much, so you can use the PVC, but what you require strength, and as well as you require very high strength like landfill construction, then what you can use the HDPE material. Now this material also, when you will join actually one with the other material, you require two kind of the testing and what will be the type of the joining. That is also very important to us. So I am showing it here that what will be the behavior of HDPE sheet and the seam. So this material you can perform the test like this, which you call the seam. It's kind of joining, seam in shear. You can see this is the material, this is geomembrane, this is geomembrane material, and there is a shear in between the material. You can join and there will be the shear. So you can perform the shear test. So you will be knowing what will be the seam value in shear and what will be the behavior of HDPE sheet and the seam. Also there is another test which you call seam in pill. So sometimes you can join like this. So this is the geomembrane material, this is geomembrane material, and then you can seam it, okay, seam in pill. It is like a pill, okay. So you can see that behavior of HDPE sheet and the seam. So this is seam in pill test. So you can perform seam in shear, you can perform seam in pill, and you can see what should be their behavior. Also there are different types of the joining system is there. Various methods available to fabricate geomembrane seam. I am just showing that some of the seam. One is called the extrusion seam. So if this is the geomembrane and this is the geomembrane, okay, and then you are this part here seaming, okay. So this called fillet. This is fillet type, okay, or you can also make it seam in this type and this. So this calls flat type. That means this extrusion seam may be the fillet type or the flat type. Also there are other three types are there. One is called the chemical fusion, which is the chemical seam. Another is called the chemical adhesive, or which you call adjacent seam. And apart from that, which is also very important to us, that is thermal fusion seam. thermal. Fusion seam. So, it is like this. So, then you are seaming like this here and seaming like this, sorry, this will be like this. So, it will be seaming like this here and here. You can see there is a hole between two geomembrane. So, this also called the dual track hot wedge. So, there is a gap. So, there will not be development of the pressure. I am showing you one like this. This is the geomembrane and this is another geomembrane, and there is a hole. Okay. So, if any pressure development can be minimized or can be reduced. So, this kind of the seaming, geomembrane seam, is essential for the construction site. So, this is very nice or very good but seaming. So, you can see that various type of the seaming, but dual track hot wedge is the best suited for the construction of any project. Now, next, the tear resistance of geomembrane as per STM D1004 or D2263, D5884, D751, D1424, D1938 and ISO 34. This specimen has a 90 degree. You can see this pictorial view. This is the geomembrane and this is the 90 degree. This is 101.6 millimeter. This is 50.8 millimeter, and this is width is about 19 millimeter. So, you have to put in a universal testing machine and you have to perform the tear resistance of geomembrane. So, this is also important because sometimes it may be tear it up. And here I am just showing that some of the geomembrane how can be joined for the seam in CR and seam in the field test. This is the machine which you can join this. That means equipment for joining the geomembrane. I have also explained some of the type of the seam geomembrane. Here this is the fusion, here is the extrusion lab, or this is the extrusion fillet. So, this is all given by after Geogrid 1994. So, hydraulic properties now. We talk about all strain related problem for the geotextile, geogrid and the geomembrane. So, this is all strain related problem. So, it may be application for the input soil wall, it may be application for slope stability problem, embankment problem, but also we want to check up the properties of the geosynthetic material in hydraulic related, coastal related problem. So, hydraulic related properties also are very important. This is flow related problem, not strain related problem. So, we have to perform that what should be the porosity of the geosynthetic material, apparent opening size, percent open area and permeability or the cross plane permeability and transmittivity or in plane permeability. So, how you can calculate the porosity? Porosity can be defined as a volume of the void by total volume. So its porosity genus by N is equal to Vb divided by V, where total volume V is equal to Vs plus Vb. Vs is equal to volume of the solid, and that is m into A by rho. M is mass per unit area, that is gram per meter square, and A is area meter square, and rho is the density gram per meter cube, and Vb is the volume of void, and V is the total volume, that is A into Tg. A is the area and Tg is the thickness of the geomembrane. So you can write N is equal to Vb by V, that means V minus Vs by V, that means 1 minus Vs by V. So 1, that means N is equal to 1 minus, this is Vs means m into A by rho, m into A by rho, this divided by your V, V is equal to A into Tg, this is A into Tg. So we can have N is equal to 1 minus m by rho into Tg. So if you know m, if you know rho, and if you know thickness of the geosynthetic material, so you can calculate the porosity. This is also very important parameter. Now next is apparent opening size, or which we call EOS, or equivalent opening size, that is called EOS. This is as per STM D4751. This parameter is very, very important for the any erosion control problem, filtration problem, drainage problem. There are various methods to measure the apparent opening size. It may be by sieving the glass beads, by image analyzer, that is Gauss ETL 1982, and by mercury intrusion, that is Holz 1988, and by bubble point method, that is Bhatia ETL 1996. So we use that glass bead. You can see here different types of the glass bead. This 2.8 millimeter, 1 millimeter, you can see different types of the glass bead, and we have conducted also the apparent opening size of the some of the material. So this is the geotextile, this inside geotextile clamp to the ship frame, and this is the pictorial view of the test procedure, and you can see this is the schematic of die sieving method. This is the vibration unit, and this is the pan, and this is the red color is the geotextile material, and this the glass bead is passing. This is on the top of this is the lid, and the size of the beads which passes by less than or equal to 5% is represented as apparent opening size of the geotextile, or O95. This you remember O95, because there are some country they use also that O90, but STM specification given O95, and this O95 is expressed as millimeter. So O95 value is specifically used for the design of any hydraulic structure. So this is very important, that how you to calculate the apparent opening size of the geotextile. We have performed some of the tests. This is this test for the apparent opening size of different geotextile material, and it has a percentage final, the y-axis, and the particle size is millimeter on the x-axis. So here this showing that weight 700 gram per meter square, and you can see this is the O95. So you can calculate what will be the particle size in millimeter. So for this weight is about 700 gram per meter square, and apparent opening size is 0.25 millimeter. And this is another sample whose weight is about 675 gram per meter square, and apparent opening size O95 you can calculate as 0.17 millimeter. You can see O95, that what I said, that only that 5% is represented. So, size of the bit which passes by less than or equal to 5% is represented as O95. So, O95 you can calculate. So, apparent opening size of the geotextile here are decreases with the increase of the geotextile, weight of the geotextile material. So, this is very important parameter. Now, percent open area. Percent open area can be defined as the ratio of total open area to total void area of the geotextile to the total area of the geotextile. It is expressed in percentage. So, percent open area can be expressed as POO, that is the total ratio of total area of opening of geotextile to total area of geotextile material. Now, the open area is measured passing a light through the geotextile to a poster size cardboard which is in the form of graph sheet. From the graph sheet, number of square can be counted. Otherwise, the void can be mapped by a planimeter. So, total area is measured by the same magnification. Now, POA is applicable only for monofilament oven geotextile. The percent open area POA for monofilament and slit film oven should be greater than or equal to 4%. As the filament of non-oven geotextile are closely tightened and very random, light cannot pass through it properly, and as a consequence, the light passing method is not suitable for it. So, it is preferable to perform the test for the oven geotextile rather than the non-oven geotextile material. I ended up this lecture here. Please let us hear from you any question. Thank you for listening.